Hi everyone, welcome to assignment 35. We're going to be doing some more work with solving today. And I want to look at multiple angles, i.e. I'm changing the b value from 1 to something else. So I'm going to do 2. Okay, but let's start with, warming up from what we're supposed to be comfortable with. How about this one? How about 2 sine squared x plus 3 sine x plus 1 equals 0. And let's talk about 0 to 2 pi. Oops, you never see a bracket there. Always a parentheses. Remember, the parenthesis means we don't include 2 pi, which means 2 pi should never be one of my answers. 2 pi should never be one of my answers. It's a really common mistake I see on the assessment for this unit, is that people, in fact, include both 0 and 2 pi. Or they don't include 0, but they do include 2 pi. Yeah, no, this notation says with the bracket, 0 is included, and with the parentheses, don't write down 2 pi. Okay, so what are your thoughts on this? Please don't say subtract 1 from both sides. You've literally had teachers telling you this for 4 years now. Stop it. It's not cool. It's not endearing. This is a factor situation. This is a trinomial. It fits the form 2x squared plus 3x plus 1. And just as you would factor this, so too I want to factor this. So let's factor. Instead of x's, we're going to have sine x's. And so now we can set each of these factors. Oops. That's better. And sine x equals negative 1. Okay, so where is the upness? Where is the y value? What angle has a y value of negative 1? Well, I know that happens on the unit circle at 3 pi over 2. And here, what angle has an upness, a y value of negative 1/2? And so x would be 7 pi over 6 and 11 pi over 6. At this point, I really need to know my unit circle values so that I can answer these questions. Okay? All right, there's number 1. Hey, what if instead we had said 2 sine squared x plus 3 sine x plus 1 equals 0, all solutions? How would that answer be different? We still get to that factored place where sine x equals negative 1/2 and sine x equals negative 1. And so in this situation, yeah, I agree. It's just going to be 7 pi over 6 plus 2 pi n, and 11 pi over 6 plus 2 pi n, and 3 pi over 2 plus 2 pi n. Okay, good. How about this one? Sine squared x minus 3 equals 0. Hey, welcome back. So I've got sine squared x equals 3, and x equals, sine x equals plus and minus square root of 3. And then I say no solution. How come? Well, think about your graph for sine. Go up to that high point and come back down. On the reference graph, y equals sine x. What is the y value here? 1. The highest sine will go as 1. Square root of 3? Well, the square root of 3 is bigger than the square root of 1. A little smaller than the square root of 4. That's the number 2. That's the number 1. Square root of 3 is between them. But since 1 is as high as I go, I can never get to root 3. Okay, so this has no solution. Now, if I change this problem a little bit, like put a coefficient here, what happens then? Well, now I've got 3 over 4 that I'm taking the square root of. And some students are stumped here. And, one of the things we've been talking about is to maybe consider breaking this up into 2 separate radicals. So we've got plus or minus root 3 over 2. When is sine equal to plus or minus root 3 over 2? Well, we know that happens at all the pi over 4s. And this would be our solution if we were on 0 to 2 pi. If we were doing all solutions, then I might be inclined to put a plus 2 pi n with each of these. But instead, why am I doing this? That's my solution. I wouldn't mark this plus 2 pi n, this plus 2 pi n, this plus 2 pi n, and this plus 2 pi n wrong. I would think there was a lot of writing, but I wouldn't mark it wrong. I noticed that all the pi over 4s are separated by pi over 2. So I can just start here and say, well, it's going to be pi over 2 to this next one, and pi over 2 to this next one, and pi over 2 to this next one, and so on. So I'm going to go with that answer. Okay. How about this one? 1 minus tangent squared beta equals 0. And I want the solutions on 0 to 2 pi. Give that one a try. Come back when you're done. Hey, welcome back. So for me, tangent squared beta equals 1 because I added tangent squared to both sides. I take the square root. Okay, now I've got tangent beta equals, don't forget the plus or minus because you took a square root. And so how am I to know this? Well, remember, tangent beta is the same as sine beta over cosine beta. And in order for this ratio to be equal to 1, these numbers have to be the same. And in order for the ratio of these to be -1, we need these to have opposite SIGNs. One is positive, one is negative. So where does that happen? Well, that happens when beta is pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. These are places where tangent is equal to -1, and these are places where tangent is equal to +1. Here, because both sine and cosine are negative. Okay? So that's what we were doing. Now tell me about this one. Sine x equals 1/2. So this should be easy peasy for you. Let's do 0 to 2 pi. And let's also do all solutions, because I'm going somewhere with this today. This is the start of the new stuff. Shouldn't be so hard. I mean, if we think about it graphically, I know that this is pi over 2. So there's one solution in first quadrant and one solution between pi over 2 and pi. That means one solution in second quadrant. And that sort of makes sense, because when I think about sine being the y value or the upness, I think, okay, I have positive 1/2 in 2 places. And that happens here at pi over 6, and here in second quadrant at 5 pi over 6. And if I'm doing all solutions, I'm just going to say x equals pi over 6 plus 2 pi n, and 5 pi over 6 plus 2 pi n. Yeah, I said it was easy. And you don't need the graph. You can just do it over here. I'm just sort of saying, sometimes it helps to have a visual understanding of what's going on, especially when teacher does this. Sine 2x equals 1/2. Okay, so this is a little different. Sine 2x equals 1/2. Well, so when I do that part about what angle has this upness, and we say pi over 6 and 5 pi over 6, yeah, there's a problem with that, in that what does this do? This divides all the x's by 2. And so now what's happened is I've taken my sine graph and I've horizontally compressed it. Oops, that's pi. That's 2 pi. And so now I'm looking at something like this. This is sine 2x. And look what's happened. When I go from 0 to 2 pi, now instead of 2 solutions, I've got 4 solutions. This number, I'm compressing by a factor of 2. Therefore, not only can I fit one set of solutions between 0 and 2 pi, but now a whole second set of solutions. And so what I'm going to say is that what we'd like to do here is the following. 1, go around the unit circle B times collecting solutions. Okay, so the first time we go around, we get that pi over 6, and we get that 5 pi over 6. And then the second time we go around, well, remember the period for sine is 2 pi. So I'm going to have to add 2 pi to this. Okay, add 2 pi to this, I get 13 pi over 6. And I've got to add 2 pi to this, which gives me 17 pi over 6. And I agree with you, this is way bigger than 2 pi. 2 pi is smaller than this one. So what's happening? Well, what we've just done here by going around the unit circle twice, that's what 2x is equal to. Solving for that. So that's what 2x is. I want to know what x is, so I have to divide everywhere by 2. And so now I've got x equals pi over 12, 5 pi over 12, 13 pi over 12, 17 pi over 12. Okay? Yeah. Now, here's the thing about going around b times. It says 2, and we went around once, and we went around a second time. Some students confuse this 2 with this is the first time they went around, and then they need to go around yet one more time. And that's not the case. This was the first time around. This is the second time around. So when that number is a 2, once around, twice around. Okay? Good. So yeah, I get these solutions, and over here, 24 pi over 12 would be 2 pi, and this is less than 24 pi over 12. So all my solutions are, in fact, between 0 and 2 pi. In fact, I could even pull out my calculator and type in sine 2x and type in 1/2. And I'm looking on 0 to 2 pi, and I'm going from -1 to 1. That's great. Okay, there's my graph. There are my 4 points of intersection. You know, one of the things I like about this from a graphical point of view is at least I know how many solutions I should be finding, right? So like if I forget about the whole going around twice thing, and I only go around once picking up solutions, maybe if I graph it, I'll see, oh, there's more solutions. How am I supposed to get those? Okay? All right, so when I'm on 0 to 2 pi, I'm going to go around the unit circle, in this case twice, picking up solutions. And then second thing I'm going to do is divide all solutions by this b value I've got, right? So we found the 4, and then we divided everyone by that b value. So if I were looking at something like sine of 3x. Why don't you show me what the solutions would be for sine 3x equals 1/2 on this interval? And then I'd like to go back and I'd like to look at the all solutions cases for these, okay? Okay, welcome back. So did you go around 3 times? If you did, you should have 3x equals pi over 6, 5 pi over 6, 13 pi over 6, 17 pi over 6, and then I've got to go around once more, so I'm adding another 12 pi over 6, and 29 pi over 6. All right, but that's what 3x equals, and we want to know what x equals, so we're going to divide everywhere by 3. So I get x equals pi over 18, 5 pi over 18, 13 pi over 18, 17 pi over 18. Oh my goodness, this is still less than halfway around the circle. We've got 17 pi over 18, 25 pi over 18, and 29 pi over 18. 36 pi over 18 would be 2 pi, and this is less than that. So these are my solutions. And speaking of using your calculator, let's go back and change this down to 3x. But now let's also change our scale. I'm going to change my x scale. See how these are all pi over 18s? Yeah, that's what I'm going to change it to, pi divided by 18. Okay, and graph. And the nice thing about choosing pi over 18s is that I could actually count. Oh, look, here's a solution at 1 pi over 18. And there's 2, 3, 4, oh, there's 5 pi over 18. And so I could actually count the solutions here. This is not a good way to do the problem and expect to get these answers. It's a way to check the answers, because here I needed to actually do the problem to know that my x scale should be 18ths. Good. So now let's go back and think about, can we do the same thing if we're talking about all solutions? Okay. So originally we would say, or even in the last video, we would say, okay, when is the y value 1/2? That happens when x equals pi over 6 and x equals 5 pi over 6. And if we were looking for all solutions, we'd say, all right, well, slap a 2 plus 2 pi n on that, and that'll be good to go, because this one, 1/2, is going to occur every time I go around another 2 pi. In fact, I could even go backwards 2 pi. And so that's great. And we've got this other opportunity here. But remember, the distance between these is 4 pi over 6, whereas the distance between these is 8 pi over 6. And since these distances aren't the same, I really do need a separate term for each one. Well, here's what I would like you not to do. When we get to that place where we're looking at sine 2x equals 1/2, and you say, okay, I know that 2x equals pi over 6, 5 pi over 6, 13 pi over 6, 17 pi over 6, and now we're saying, ooh, let's divide all of those. And now we've got these pi over 12s. So here's what's happening. Yes. No. And then 5 pi over 12, and 13 pi over 12, and 17 pi over 12. And it's here that students are now slapping on the plus 2 pi. And I want to, have a conversation about this for a moment. Saying this is an awful lot of overkill. Instead, I want to say that when we have all solutions, we don't go around the unit circle that many times picking up solutions. No, we don't. This is different. So I want to make note of it. 1, go around only once. That's it, just go around once. Go around once. slap on the plus 2 pi n. And step 3, divide all solutions by the b value. And what do I mean by that? Well, so if we're doing this problem here, and we have these answers, okay? So what I'm suggesting is divide by 2, but wait, there's more. Divide by 2, divide by 2, divide by 2, divide by 2. And so my answers here are going to be x equals pi over 12 plus pi n, and 5 pi over 12 plus pi n. I shouldn't be seeing 2 pi n's here. Yeah. Okay, so why don't you try doing 3? Sine of 3x. Remember, you're only going to go around once. This is different. With all solutions, we just go around once. 0 to 2 pi, we go around that many times. But on all solutions, just go around once. Hey, how did it turn out? Did it go well? Hope so. Let's see. So we knew that sine of 3x was equal to 1/2. And I know since I'm doing all solutions, I'm only going to go around one time picking up solutions. Pi over 6 plus 2 pi n. Pi over 6 plus 2 pi n. That's so nice. Only once around with all solutions. And then divide by 3 everywhere. And so I'm going to end up with x equals pi over 18 plus 2 pi n over 3, or 2/3 pi n, and 5 pi over 18 plus 2/3 pi n. This is a lot less work and a lot less writing. You only have to go around once. I would recommend doing that. Now, that being said, you can't do that with 0 to 2 pi solutions. Okay? All right, so why don't we try this one then? Why don't we try and go through this one? Cosine theta equals negative root 2 over 2. And I would like all solutions. No, I would like 0 to 2 pi and all solutions. So what do you get? Pause the video, write it down, and then we'll move on to the next one. Hey, welcome back. So when is cosine negative root 2 over 2? Well, those happen in second and third quadrant. And so I know that theta equals 3 pi over 4 and 5 pi over 4. If I want all solutions, no worries. 3 pi over 4 plus 2 pi n, and 5 pi over 4 plus 2 pi n. And I'm all good and done. Okay? But, because we knew this wasn't the stopping place, what if I have 2 theta? So, will you please show me the 0 to 2 pi solutions, as well as the all solutions for cosine 2 theta? Pause the video now and go through that, please. Hey, welcome back. So, cosine is equal to negative root 2 over 2. Well, I know that happens at 3 pi over 4 and 5 pi over 4. But I have to go around another time, so I'm going to add 2 pi to this, which is 8 pi over 4. So 8 plus 3 is 11 pi over 4. And if I add 8 pi over 4 here, I'll get 13 pi over 4. These aren't my solutions yet, because that's just what 2 theta is. I want to know what theta is, so I'm going to divide everywhere by 2. And so theta equals 3 pi over 8, 5 pi over 8, 11 pi over 8, and 13 pi over 8. Those are my 4 solutions on 0 to 2 pi. But now what about all solutions? Well, remember, with all solutions, I don't go around the unit circle twice. picking up solutions, I just go around once. 2 theta equals 3 pi over 4 and 5 pi over 4. Don't forget those plus 2 pi n's, but now divide everywhere by 2. And so we get 3 pi over 8 plus pi n, and we get 5 pi over 8 plus pi n. So here I have to go around the unit circle that many times. This is the first time. This is the second time. Many students think this is the first time, but that's not correct, because where did these come from? It's not I'm going to go around once and then 2 more times. It's just I'm going to go around once and a second time. Okay? And if I'm doing all solutions, I only go around once, I slap on the plus 2 pi n's, and I divide everywhere by that b value. I can't ignore dividing here by that b value. So please make sure that gets done as well. Okay, last one of these. Change it to a 3 and show me what these are. Okay? Hey there. So, when does cosine equal negative root 2 over 2 and go around 3 times? Okay, 3 theta equals 3 pi over 4, 5 pi over 4, 11 pi over 4, 13 pi over 4. I'm adding 2 pi to this now, so that's 8 pi over 4, 19 pi over 4, and if I add 8, 21 pi over 4. But that's 3 theta, theta, and so I'm going to divide everywhere by 3. 3 pi over 12, 5 pi over 12, 11 pi over 12, 13 pi over 12, 19 pi over 12, and 21 pi over 12. And sure, you can simplify this fraction. I'm not gonna. If for no other reason than if I want to check my answer with my calculator and I want to set the x scale to be pi over 12s, it's easier for me to see, oh look, I count over 3 pi over 12s, and that was one of the solutions. If I turn that into pi over 4, it's going to be maybe a little more thinking for me to do. So here's the 0 to 2 pi solution. And look, think about it also this way. Cosine is the x value. The x value is negative in 2 quadrants, quadrant 2, quadrant 3. So every time I go around the unit circle, I should pick up 2 solutions. Once around, twice around, 3 times around. So I should end up with these 6. Now, what about the all solutions case? Well, with all solutions, we only go around once. 3 theta equals 3 pi over 4, 5 pi over 4. Now we slap on the plus 2 pi n's, and then we go and divide everything. It's funny because people divide here by 3 and then don't divide here by 3. You really need to divide here by 3. Dividing here by 3 is picking up these and these. If I don't divide these by 3, then I'm skipping these others. And I don't do that. So theta equals 3 pi over 12 plus 2 thirds pi n, and 5 pi over 12 plus 2 pi over 3. Okay? All right. Well, I hope that's feeling a little more comfortable and confident for you. The rest of the problems that I want to look at pretty much fall into just the practice category for a little bit, but then there's just one technique that I want to show you, one additional technique. So let's see what happens. How about this? 7 cosine 2 theta plus 9 equals negative 2 cosine 2 theta. So what are we going to do? Oh, and let's do 0 to 2 pi. Okay. So what's your recommendation? And some people are very comfortable here saying, well, I'm going to add 2 cosine 2 theta to both sides. because here I've got some cosine 2 thetas as well. And that's cool. You could subtract this over. Some people are just kind of stuck here. So let me say x equals cosine 2 theta. And now let's rewrite this equation. It would be 7x plus 9 equals negative 2x. So how would you solve this equation? Right? Well, some would subtract 7x from both sides, and some would add 2x to both sides. It doesn't matter what you do, but that's what we're looking at here. We're looking at this pattern. We're looking at this situation. I'm going to try and get the trig functions all to one side. So I'm going to actually subtract 7 cosine 2 theta. And so that's going to give me 9 equals minus 2 of these things minus 7 of the same thing is going to be minus 9 of those things. Please notice that this did not change. It's not cosine 2 theta, cosine 2 theta, cosine 4 theta. No. It's minus 2 of these things minus 7 of these things gives me minus 9 of these things. And now I'm going to divide both sides by negative 9. I'll get negative 1 equals cosine 2 theta. I know I'm looking for solutions on 0 to 2 pi. Because I see this, I know I'm going to go around twice. Okay, first time I go around, I get pi. Cosine, the x value is equal to negative 1, only at pi. So then I add 2 pi to that, and now I've got 3 pi. Don't forget to divide everywhere by that b value. So theta equals pi over 2, and 3 pi over 2. Any questions about that? Okay. How would this be different if instead of 0 to 2 pi, we said all solutions? How would that be different? Well, I'd still do this. I'd still do this. I'd still have this. But at this point, I would only go around the unit circle once. So I'm not going to have that. Only go around once. Let's back up to that. 2 theta equals pi. I went around once and I got that. I slap on the plus 2 pi n, and now I divide everywhere by 2. So theta equals pi over 2 plus pi n. Okay? Hey, let's take a look at another tangenty one. There's something I want to remind us of with tangent things. How about tangent 3x equals negative 1. Okay. And again, I'm looking, no, I want all solutions. No, let's do 0 to 2 pi. We can start the conversation now. Okay, so when is tangent equal to negative 1? Tangent is equal to negative 1 in second quadrant and in fourth quadrant. So we're looking at 3 pi over 4 and 5 pi over 4. Okay, so think about what's happening here. One of our solutions is here, and another one is here. And this is 3 pi over 4. I guess that's 7 pi over 4. Gosh, I really appreciate when I graph these things, the things that I see. And we know that the distance from here to here is pi, and the distance from here to here is pi. And the thing I wanted to remind you of that we talked about during our trig graphing, the period for tangent is pi. So these answers are pi apart. And that means that when I get to, I guess I'm going to move there now. I'm looking at this, and I think, okay, I'll divide, oops, no, I'll go around this many times picking up solutions. Well, I'm not adding 2 pi to this. I guess I could, but I kind of want to say that, tangent, this is pi over 2 This is 3 pi over 2. This is 5 pi over 2. And this is 7 pi over 2. Yeah, so we're wondering when this is equal to -1. And so I see this one at 3 pi over 4, and this one at 7 pi over 4. And I guess you could say that's one surrounding unit circle. But the distance between these answers is always pi. So I guess I could just keep adding pi to this. And if I'm picking up two solutions the first time I go around, I'm going to go around 3 times. I should have 6 solutions when I'm done. And I can get those 6 solutions by just adding pi to each of these. 11 pi over 4, 15 pi over 4, 15 pi over 4, and 23 pi over 4. Now if I divide everywhere by 3, I'm looking at x equals 3 pi over 12, 7 pi over 12, 11 pi over 12, 15 pi over 12, 19 pi over 12, and 23 pi over 12. 24 pi over 12 would be 2 pi, so this is just a little less than 2 pi. Well, that's great. How would I do this problem differently if this said all solutions? Well, instead of slapping on plus 2 pi n, because the period of this function is not 2 pi, what I'm going to be doing here is slapping on plus pi n. The period for tangent is pi. So I got 3 pi over 4, I got 7 pi over 4. I add plus pi n. I strongly encourage you to make a note about this in your notebook. That plus pi n for tangent and cotangent problems. This is a plus 2 pi n for sine, cosine, secant, cosecant problems. But for tangent and cotangent, this needs to be plus pi n. Period of tangent is plus pi n. In fact, wait a second, how far is it from this solution to this solution? Well, it's pi. So really, in order to not be redundant, I'm just going to use that. Yes, I'll go and talk to you about that, but wait a minute. So my answer should be x equals pi over 4 plus pi over 3. So student said, hey, can't I just do my plus 2 pi n's? Oh, no, sorry. First student was wondering, couldn't they just write both with plus pi n? Okay, 3, 3, 3, 3. And so what did they end up with? They got 3 pi over 12 plus pi over 3 n. And they got 7 pi over 12 plus pi over 3. So let's see if that generates here. Well, this we know would be 3 pi over 12. Okay? So we definitely have that first answer. Now, if I plug a 0 here, that's this. If I plug a 1 in here, I'm going to get adding, I'm going to add another 4 pi over 12. And so 3 pi over 12 plus 4 pi over 12 is 7 pi over 12. So yeah, with this approach where I'm going to write both of them, I'm going to go around 0 to 2 pi once, picking up solutions, put on the plus pi n's, and then divide by 3. I get those values. I can get the correct values here. It's just that all of these are already made by this stuff. So I'm just sort of duplicating everything with this second solution. But what happens if we try and do the plus 2 pi n? Okay, so we're looking at we're looking now at 3 pi over 4 plus 2 pi n, and 7 pi over 4 plus 2 pi. Okay, and I'm dividing by 3. Okay, so now I've got 3 pi over 12 plus 2 pi n over 3. And for the purposes of this experiment, I'm going to turn these both into 12ths. So this is 8 pi over 12. Okay, and here we have 7 pi over 12 plus 8 pi n over 12. All right, so did these also get, so it's a plus, did these also get all our solutions that we saw? Well, the tidy one was pi over 4 plus pi over 3n. And if I make the common denominator, I'm looking at 3 pi over 4 plus 4 pi, oops, stop. Okay, this is 3 pi over 4 plus pi over 3. I want to make 12ths. I want to make 12ths, so I'm going to get a common denominator. It's 9 pi over 12 plus 4 pi over 12. And there's a okay. So if I plug a 0 in here, I get 9 pi over 12. I can't get 9 pi over 12. Okay. If I plug in a 0 here, I get 3 pi over 12. If I plug a negative 1 in here, that's minus 8. That's minus 5 pi over 12. Yeah, I'm not getting the solutions. So no, don't slap the plus 2 pi on. It really does matter. Don't slap plus 2 pi on tangent or cotangent. That's probably very noteworthy, box and highlighter worthy. Okay. All right. How about this problem? 4 cosine squared 3 theta equals 1. So you that equation. And, let's do 0 to 2 pi. Okay. How'd it go? I hope that you said that cosine squared is equal to 1/4. And then you took the square root, because you've got to deal with that before you deal with that. So cosine 3 theta is going to be plus and minus square root of 1/4, which doesn't help a lot of people. It really helps to write that as plus and minus square root of 1 over plus and minus square root of 4. Because when people do this, they see, oh, that means cosine 3 theta should be equal to plus and minus 1 over 2. Okay, well, I can figure that out. I mean, I know that cosine is 1/2 here at pi over 3, and negative 1/2 here at pi 2 pi over 3. And here at 4 pi over 3, we have cosine equal to negative 1/2. And again, cosine is positive 1/2 here at 5 pi over 3. And so I'm saying 3 theta is pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. However, I have to go around 3 times picking up solutions. So I'm going to add 2 pi to each of these. 2 pi is going to be 6 pi over 3. So 7 pi over 3, 8 pi over 3, 10 pi over 3, and 11 pi over 3. But that's the second time around. I need to go 3 times around. So I'm going to still have some more. I'm adding 6 pi over 3 to this, 13 pi over 3, 14 pi over 3, 13 pi, no, 16 pi over 3, and 17 pi over 3. But that's 3 theta, and I want theta, so I'm going to have to divide all of these answers by 3. I'm going to have pi over 9, 2 pi over 9, 4 pi over 9, 5 pi over 9, 7 pi over 9, 8 pi over 9, 10 pi over 9. Gosh, there are a lot of solutions. 11 pi over 9. And then we're going to have these over 9 as well. 9, 9, 9. And this is a little less than 18 pi over 9, which would be 2 pi. Look at all those solutions. Well, let's think about why there are so many. Okay. This cosine is positive twice. Okay. Cosine is negative twice. So the positive is giving me 2 solutions. The negative is giving me 2 solutions. So I get a total of 4 solutions with once around. But I'm going 3 times around. So I should have 12 solutions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Ta-da! Okay? Okay. Hey, what happens if I change this problem just a little bit? What if I make it 4 secant squared 3 theta equals 0? Equals 0? Did I mean that correctly? Sorry, I'm missing something. There we go. There needed to be a minus. A minus 1. Yeah. Okay. Okay, so, and yeah, let's look on 0 to 2 pi. Okay, so I divide both sides. Oh, I add 1 to both sides and then divide by 4. Secant squared 3 theta equals 1/4. We'll take the square root, and we've got secant 3 theta equals plus and minus square root of 1 over square root of 2, or plus and minus 1/2. Good. Now what? Well, I don't recognize that. Like, I don't know my secant values. But I do recognize that is the reciprocal of the plus and minus 2 over 1. And so what can we say about that? Well, if we think about the situation graphically, let's go back to here for a minute. Our secant graph. Remember, our secant graph comes from cosine. And whenever cosine was equal to 0, or crossed the sinusoidal axis, we could draw in our secant graph. Well, the y value here is 1, and the y value here is negative 1. When are we going to have a y value of 1/2 or negative 1/2 with secant? Well, here's 1/2. Secant never gets that low. Here's negative 1/2. No, secant doesn't get there. So this is no solution. And if we don't catch it here, we can certainly catch it here. Cosine equal to 2. No, the highest cosine gets is 1, not 2. So this is no solution. Okay? And you could certainly have that. Okay. Oh yeah, so, sorry. I got distracted by Ian's texting group me. Plus cosine x equals 1. All right, so solving this. Um, you know, let's do it on both 0 to 2 pi and all solutions, but let's start with 0 to 2 pi. Okay, so generally what I see students do is this. I see some students say, well, sine x equals 1 and cosine x equals 1. No, I can't make that statement. This is a plus symbol. Now, if I had the problem sine x times cosine x equals 1, maybe I could think about, but no. Well, yeah, so I could think about setting each of these equal to 1, but that whole thing about setting factors equal to 0 means that those things, and I have a 0, and then I can set the factor equal to 0. And I'm not sure that's what we were just looking at. Okay, in fact, I'm really sure we're not. So some students say, well, how about we isolate the sign? And we've got 1 minus cosine. So then that student usually does, hey, let's do the inverse sign. And then they start crying over here. So no, we're not going to do that. So what are we going to do in Euclid? Well, what we're going to do is square both sides. I'm going to square both sides. There. Okay, so we've got a foiling situation, and that's the second thing. Like even students who know to square both sides don't foil here. What they end up doing is they apply that exponent, so they have sine squared plus cosine squared equals 1, and they say, oh yeah, that's the Pythagorean identity, and then they don't know how to solve that. So here's what I want to say. I want to say this is FOIL. This is sine x plus cosine x times sine x plus cosine x. And that's FOILing. That gives us sine squared plus sine x cosine x plus sine x cosine x plus cosine squared equals 1. I can combine like terms. So I've got 2 sine x cosine x. And over here, sine squared plus cosine squared, well, that's 1. And then I can subtract 1 from both sides. And now I've got this. And you know, divide both sides by 2, you'll be happier. And so now we're at this place. We're at the place where the problem says sine x cosine x equals 0. Well, great. I can set this factor equal to 0 and this factor equal to 0. And so when is sine equal to 0? Well, at x equals 0 and x equals pi. And don't write that. Why not? Because that's not included. If you write that 2 pi, we have to mark it wrong. Cosine is 0. Pi over 2, 3 pi over 2. And there are 4 solutions to this. Just there. Gotcha. Okay. All right. So why don't you do one similar to this? How about this one? Oh, should we do all solutions first? Yeah, let's while we have that, we had sine equal to 0 and cosine equal to 0, and so we had x equals pi over 2. No, pi 0 and pi. And over here we had x equals pi over 2 and 3 pi over 2. And if we wanted all solutions, yes, you could slap on the plus 2 pi m. Oops. But really, think about these solutions. You've got these solutions, and you've got these solutions. At the very least, 0 plus pi m, and that will take care of that. And from here to here and here to here, pi over 2 plus pi m. But ideally, I mean, I'd love to see 0 plus pi over 2n, because from here to here is pi over 2, here to here is pi over 2, here to here is pi over 2, and here to here is pi over 2. And in fact, you could just put that. Yeah. But no, we wouldn't mark it wrong if you gave us this one. I understand. Mr. Paz understands. It's not wrong. It's just a lot of work. You'd be happily doing a lot of work. And we respect that desire on your part. Okay, so how about this one? How about tangent x plus secant x equals 1? Please solve this. Okay, well, did you square both sides? Yeah, did you square both sides? Or did you do this? Oh, I wonder if you did this. I wonder if you said that's sine x over cosine x plus 1 over cosine x equals 1. And so you had sine x plus 1 over cosine x equals 1. Sure, there's nothing wrong with that so far. Then people do this. They multiply both sides by cosine. And they end up with sine x plus 1 equals cosine x. And they don't know where to go from there. And that was the problem kind of we just showed, where you have to, if you're here, you can square both sides. Okay, so let's go square both sides. I'm a little concerned about squaring both sides because I don't have this as an identity. I do have secant squared minus tangent squared equals 1. So I'm kind of wondering what this will turn out to be. But first the FOIL, right? Because we've got tangent x plus secant x times tangent x plus secant x. So we've got tangent squared x plus tan x secant x plus another tan x secant x plus a secant squared x equals 1. Okay, I can do the combining like terms thing. Tangent squared x plus secant squared x plus 2 tan x secant x equals 1. Okay, well, now what? Well, if I bring this over here, secant squared minus 1 is very good tangent squared. And so tangent squared plus tangent squared is now 2 tangent squared. So now I've got 2 tangent squared x plus 2 tangent x secant x equals 0. And from here, I'm able to factor out a 2 tangent x, leaving me with tangent x plus secant x equals 0. Well, now I've got 2 tangent x equals 0. And over here, I have something that feels very much like where I started the problem, except that this was equal to 1, and this is equal to 0. And I can do stuff with 0 that I couldn't do with 1. First, over here, when is tangent equal to 0? Tangent is equal to 0 at 0 and pi. Ooh, let's do 0 there, 2 pi. Okay. Now, here. Okay, so I could always subtract a secant and ask when is the tangent graph equal to the secant graph. But people are generally happier doing this. Sin x plus 1 over cosine x equals 0. The problem with doing this is that sometimes when you multiply both sides by this denominator, you're actually throwing solutions away. And let's check this by doing this problem a second way to see if this is one of those situations. So I'm going to end up with sine plus 1 equals 0. And so sine x equals negative 1. And so I get x equals 3 pi over 2. Only one solution here. But let's try this other approach where we subtract secant from both sides. Okay, and so now I've got sine x over cosine x equals negative 1 over cosine x. No, that's going to get the same 3 pi over 2 answer. I feel like I'm missing something here. We tried multiplying both sides. Well, here's the way I'm going to confirm what I know. I think I have these solutions, so I'm going to graph tangent x plus 1 divided by cosine x, and I'm going to graph 1, and I'm going from 0 to 2 pi, and steps out pi over 2, and I want this equal to 1, so I'm going to go up to 2. Well, isn't that special? Mr. Kukla, I only see one point of intersection. This one's at 2 pi, so it doesn't count. So x equals 0 should be my only answer. Well, I agree. And let me ask you this question, which you were not at all expecting me to ask you. Why is this a must-check problem? I squared both sides. I squared both sides. And because I squared both sides of the equation, I have to look for extraneous solutions. And it turns out that those are extraneous. If I plug pi in here, tangent of pi is 0, secant of pi, what's the secant of pi? Secant of pi, cosine of pi is negative 1. Yeah, it's negative 1. So I get 0 plus negative 1 equals 1. Well, that doesn't work. And 3 pi over 2? Tangent is undefined at 3 pi over 2. And this is 1. But 1 plus undefined does not equal 1. So, yeah, only one solution. Must check. Who would have thought? Yeah, must check. Okay, it's not as big a deal as you're worried about, so don't stress too much about it. All right, how about the last problem today? We do this one. Cosine squared x plus 2 cosine x minus 3 equals 0. And we solve this on 0 to 2 pi. Hey, how did it go? Did you factor? Cosine x 3 plus minus 1, 0. Right, this is how it factors. Minus 1 plus 3 gives me that. This gives me that. Yep, that's the factored form. So cosine x equals 1, and cosine x equals negative 3. Cosine is equal to 1 when x equals 0, and cosine is equal to negative 3. Nope, that never happens. You know your cosine graph goes to 1 and negative 1. Never going to get to negative 3. So we've only got one solution. There you go. Don't forget all these things. I think you guys are fabulous. I hope you have a wonderful day. Take care. See you in the next.